Dr. Vimlathitan Rathina Sabapati, Professor and Head of the Department of Electronics and Communication Engineering in Aditya Institute of Technology, Coimbatore. Doctorate in the field of crypt analysis in Government College of Technology, Coimbatore. Postdoctoral Fellow in the Department of Information Engineering, University of Padova, Italy. He is very much interested in research area of cryptography, crypt analysis, electromagnetic interference, compatibility, antenna design, wireless sensor network and communication. He has published papers in international journals and international national conferences. He is a reviewer of journals like DRDO, WSEAS, International Journal of Network Security, and also have a membership in professional bodies like CRSI, IACR, and Computer Society of India.
Welcome to UGC lecture series Communication Electronics for Applied Electronics. In the last session, we had discussed about the generation of FM for narrowband and wideband. In this session, we are going to see about the generation of FM using direct method and indirect method. Direct method, the carrier frequency of the carrier is varied directly by the modulating signal. This means that the instantaneous frequency deviation is directly proportional to the amplitude of the modulating signal. There are two types of direct method here, reactance tube modulator and varactor diode modulator. Reactance tube modulator, this is a simple circuit that shows the reactance modulator. This is a FET, and here between the terminal A and B we have to apply the modulating signal, and at the input side we have one capacitor and resistor. This entire circuit forms a reactance tube modulator, and here we assume that the reactance of the capacitance should be very high when compared to R. Also, the voltage Vg is nothing but the gate to source voltage. Now, we will see how the reactance modulator is used to generate an FM signal. Before that, we will see a simple concept of tank circuit. Let us consider a tank circuit which is nothing but a parallel combination of L and C. The resonant frequency of the tank circuit is 1 by 2 pi root L C. This Fr is the oscillating frequency or resonant frequency of this circuit. This depends on two components L and C. If C is increased, Fr will be decreased. If C is decreased, then Fr will be increased. That is, the resonant frequency is inversely proportional to the capacitance. In the same way, if you take the inductor L and the frequency Fr, if L increases, Fr decreases. If L decreases, the inductance decreases, Fr increases. But here we have used a fixed value of C and fixed value of L. So, the resonant frequency will be fixed. Instead of using a fixed L or fixed C, if we use a variable element, let us take C is variable. So, we can easily vary this frequency. So, here C becomes variable. We can easily vary the frequency by varying this component, but now we are going to generate a frequency modulated signal. What is frequency modulated signal? The frequency of the carrier is varied in accordance with the message signal amplitude. But here in the tank circuit, the frequency of the tank circuit is varied in accordance with the elements either L or C. For example, let us consider C. If the tank circuit frequency varies with respect to C, but in case of frequency modulation, the frequency should vary with respect to the message signal amplitude. Now, if we design a circuit which converts or which depends on the voltage, for example, if you construct a circuit whose capacitance is variable with respect to the applied voltage, for example, let us consider a capacitor. The capacitor is variable. We are constructing a circuit and we are applying a variable voltage to this circuit. If this variable voltage varies the reactance, that may be a capacitive reactance or inductive reactance of the circuit, that is called as variable reactor. Now, if we connect this variable reactor to the tank circuit, for example, if this is a capacitance, variable reactance capacitance, if we connect this circuit in the tank circuit, now what happens? We are applying a voltage which varies the reactance, which varies the reactance, and this variable reactance is connected in the tank circuit. Now, what about the resonant frequency? Let us say this is L, this is a C. This application of voltage varies the capacitive reactance. This variable capacitance varies the resonant frequency. So, this voltage varies the resonant frequency. So, this is in accordance with the frequency modulation. So, we can easily generate a frequency modulation signal using this technique. So, this is called as direct method. This circuit is a variable reactance circuit, and here for the terminal A and B we have to apply the modulating voltage, and now we will see how this circuit act as a variable reactance, and then how to connect this circuit to the tank circuit, and then how to generate an FM signal. As it says that it behaves as a reactance across the terminal A B for a particular voltage. The terminals A B of the circuit may be connected across the tuned circuit or tank circuit of the oscillator to get the frequency modulated output. The varying voltage V across the terminals A B changes the reactance of the FET. This change in reactance may be inductive or capacitive, and then this can be used in frequency modulation. Now, let us analyze. Here, neglecting the gate current, let us consider the current through this terminal is very minimum, or we can neglect the current. So, the current through the capacitance will be same as that of the current through the resistance, both current will be same. At the carrier frequency, the reactance, that is the capacitive reactance, is much larger than R. So, based on these two assumptions, we are going to analyze this circuit. We are applying the voltage V, and now we want to compute the current through this capacitance and the resistance. Let us consider I1. We know that the current is the ratio of voltage to the impedance. Here these two are connected in series. Since the current drawn by this terminal is very minimum, we can consider these two connected in series. So, what about the impedance of this series circuit? R plus the capacitive reactance. So, R plus 1 by j omega c, this is the capacitive reactance. So, the current through the capacitance or the resistance is given by this expression V by R plus 1 by j omega c. And if we consider this current I1 which is flowing through the capacitance, which can be written as I1 as j omega c into V, and if we consider this one, the current through the resistance, this I1 is nothing but Vg by R. since the voltage applied across the resistance is Vg. And now Id, the drain current. So, from the theory of this FET, we know that the drain current is nothing but the product of Gm, that is the transconductance, and Vgs, that is the voltage Vgs, which we consider here it is Vg, and Gm is the transconductance of this device. And now we are going to compute this output current Id, which is nothing but Gm into Vgs, and which is nothing but Gm into Vg. We want to find out the impedance of this circuit, the impedance of this circuit. So, the applied voltage is V and the current drawn by this circuit is I, which is Id here, and if we find out the ratio of V by Id, that gives the impedance of this circuit. V is the applied voltage and Id is the drain current. So, we are substituting the value of Id, V by Id. So, Id is nothing but Gm into Vg. So, Vg is nothing but, from this expression it is j omega CRV. So, j omega Gm into CRV. Now, for simplification, we are combining this parameter Gm into C into R. So, this is the final impedance 1 by j omega C equivalent. So, this says that the impedance of the circuit considered is purely capacitive. We have assumed that Xc is greater than R, and then we have assumed Vg equal to Vgs, and also we have assumed that the current drawn by the device FET is very minimum. Based on these assumptions, the impedance of this circuit is purely capacitive. Of course, we can make this circuit to be purely inductive also by using different assumptions. And here this C equivalent depends on 3 parameters Gm, C, R. These 2 values are determined by the users. So, C and R are fixed by the users, and this Gm, which is nothing but the transconductance, that depends on the device selected. Of course, here if we consider the unit of these 3, if we take the product of these 3, the unit of this Gm is Siemens, and the unit of the capacitance is Farad, and the unit of this resistance is ohms. If we take the product of these 3, Siemens and ohms gets cancelled. So, the unit of the C equivalent will be again Farad, that it says that it is purely capacitive. Z is the impedance of the FET. By varying the modulating voltage across the FET, the operating point Gm can be varied, that is we can vary the transconductance Gm. If we vary the Gm, we can vary the C equivalent, which is nothing but the product of Gm, C and R. By varying the applied voltage, we can vary the impedance, that is the capacitive reactance. Hence, the modulating voltage varies the equivalent capacitance. If we connect this entire circuit across the tank circuit, then by varying the applied voltage, we can vary the reactance of this circuit, thereby we can vary the resonant frequency of the tank circuit, thereby we can easily generate a frequency modulated wave. Usually the capacitive reactance Xc should be greater than R, and here we assume that Xc is greater than R and the ratio, that is Xc should be at least 5 to 10 times of the resistance in order to have that impedance to be purely capacitive. Let us have a short break. Welcome back after the break. Now, we will see the advantages of the reactance tube modulator. It produces enough frequency deviation and requires no frequency multiplication. Because of the FET characteristics, the linear relationship can be achieved between the modulating voltage and the transconductance. That is, if the voltage is varied, then the capacitance or the variable reactance should properly follow the variation of the voltage. In order to establish a linear relationship, this can be easily achieved using the FET. The disadvantage of this reactance tube modulator. Here we are using the lumped components like the resistance, capacitance, also we can use an inductance in the circuit. The stability is poor. What is the frequency stability? For example, if the output frequency is 100 megahertz, an FM transmitter is designed for 100 megahertz with the 0.1 megahertz deviation or 100 kilohertz deviation. Here this carrier frequency should be exactly 100. If we use the low quality components, it is very difficult to achieve this 100 megahertz. The frequency may be 99.99 megahertz. See the difference. Though the value is very small, but this deviation will affect the entire modulation system. So, we have to use a high quality component in order to have high frequency stability. Application of this reactance tube modulator is they are used for low modulation index applications. The next one is varactor diode, the other way of generating the frequency modulated signal. Varactor diode is nothing but a semiconductor diode whose reactance, specifically capacitance, varies linearly with the applied voltage when the diode is reverse biased. Varactor diode are employed together with the reactance modulator to provide an automatic frequency correction for an FM transmitter. This is the symbol for a varactor diode. So, here this says that the variable capacitance. If we reverse bias this diode, then based on the applied voltage the capacitance will vary. This is the simple concept of varactor diode. We have already seen that if we connect any variable reactance element in the tank circuit, it is a variable reactance element. Here we are going to connect this varactor diode, and if we have reverse bias this diode, now what happens? The reactance of this element, that is capacitive reactance, is varied in accordance with the applied voltage. And here one important point to be noted here is this device has to be reverse biased. Now we can easily generate a frequency modulated signal using this varactor diode by simply connecting in the tank circuit. This is the circuit diagram for a varactor diode. Here we have the varactor diode, here we have the mic, audio frequency amplifier, one capacitor and RF choke, and here we have a voltage divider network, and here we have the tank circuit, and here this output of this is connected to the carrier oscillator. The variation in the capacitance of this diode are wide and linear. The varactor diode provides the junction capacitance in the range of 1 to 200 picofarad. The L1 and the C1 form the tank circuit of the carrier oscillator, that is the inductor and the capacitor forms the tank circuit. The capacitance of the varactor diode depends on the fixed bias set by the R1 and R2 without any input. We are not providing any input here. So, this bias network a voltage divider network will determine the biasing for the varactor diode. Once if we apply the message signal through a mic, then this signal will get added with this biased voltage and then that is applied to the varactor diode. Either R1 or R2 can be made variable, so that the center frequency can be adjusted over a narrow range. This one, either this one or this one can be made variable. Why we are making variable? In order to adjust the carrier frequency. If we vary the voltage, then the bias applied to this device will be varied. So, thereby the reactance will be varied. So, thereby we can vary the carrier frequency. And here we have an inductor, this acts as an RF choke, the radio frequency choke. Usually the radio frequency choke has high resistance to the high frequency, that is the radio frequency choke will pass only low frequency component and it will eliminate high frequency component. This radio frequency choke has high reactance at the carrier frequency to prevent the carrier signal getting into the modulating circuit. That is, there may be possibility of this high frequency signal to go back. If the impedance is not properly matched, then the high frequency may be reflected and it may go back to the source. So, this can be avoided using this RF choke. This isolates the output reaching the input. This RF choke isolates the output reaching the input. At positive going modulating signal, it is added to the reverse bias applied to the varactor diode, which decreases the capacitance, thereby increases the carrier frequency. A negative going modulating signal subtracts from the bias and increases the capacitance, which decreases the carrier frequency. The frequency of the LC oscillator changes due to temperature effects also. Hence, crystals can be used in FM generators to provide high frequency stability. That is, the frequency of LC oscillator is low when compared to the stability of crystal oscillators. Advantage of this varactor diode: they are simple to use and reliable, and the stability of this crystal oscillator, they have high stability. And the disadvantage, the peak frequency deviation is limited to relatively small values. Applications, they are used for low modulation index applications, and they are used for two-way mobile radio, and they are also used for automatic frequency control circuit in remote tuning. The disadvantage of this direct method, the frequency is not stable enough for communication or broadcast purpose and needs stabilization. That is, as we already discussed, the stability, that is the frequency stability, should be very high. In case of broadcasting, if we need 100 megahertz carrier frequency, then it should be exactly 100 megahertz, otherwise it will create lot of issues at the receiver side. So, here this direct method have low stabilization in frequency. So, a separate stabilization is to be provided for this direct method. The next one is indirect method. In case of indirect method, a narrowband FM is generated first and frequency multiplication is applied to increase the frequency deviation to the desired level. This indirect method is almost same as that of a wideband FM. In case of wideband FM, how it is generated? First, a narrowband FM is generated, and then using multipliers, that is frequency multipliers, we are changing the frequency, and then using certain filters we can easily extract the required frequency. So, this is the indirect method. It is almost same as that of wideband FM generation. The method here used is Armstrong method. The message signal is passed through the integrator, basically it is a low pass filter, and it is passed through a narrowband phase modulator. That is, the integrator along with that phase modulator generates a frequency modulated wave. In the same way, if we pass through a differentiator, if we pass the message signal through a differentiator and FM modulator, we can generate phase modulated signal. This is a differentiator, a frequency modulator, we can easily generate a phase modulated signal. The message signal is passed through an integrator, which is a low pass filter, which is again passed through a narrowband phase modulator, and for this narrowband phase modulator the another input is taken from the crystal controlled oscillator. The output will be a narrowband FM, and here using the frequency multiplier we can multiply the frequency, and using filters we can take the wideband signal. This is the another method of generating an FM signal. The narrowband FM wave is generated using narrowband phase modulator and an oscillator. The narrowband FM wave is then passed through a frequency multiplier to obtain the wideband FM. The crystal control oscillator provides good frequency stability, but this scheme does not provide the desired frequency deviation and the carrier frequency at the same time. The above problem can be easily solved by using multiple stages of frequency multiplier and mixer stage. Conclusion: in the today's session we have discussed about the generation of frequency modulated signal using direct method and indirect method. In direct method we have used the variable reactance method. For example, a FET is used as a variable reactor. Also we have seen how a diode, that is varactor diode, is used to generate a frequency modulated signal. In both the cases the reactance is varied in accordance with the message signal amplitude. If this variable reactance is connected in the tank circuit, we can easily vary the output frequency of the oscillator. So, the output frequency of the oscillator varies in accordance with the message signal. This generates an FM, and we have discussed about the indirect method of generating FM using Armstrong method. Let us have a simple questions. How FM can be generated using direct method, and explain how the tank circuit frequency is varied using variable reactance. Thank you.